Welcome back guys. Now in this video let's discuss about the resting membrane potential. In later videos we can discuss about what exactly is action potential, but for now let's see what exactly is resting membrane potential and what is the reason for the development of this resting membrane potential and what is the reason for the maintenance of this resting membrane potential. Okay, first of all, write resting membrane potential. Okay, so you will be having a doubt what exactly is this resting membrane potential, sir. See, resting membrane potential means the potential difference, okay, difference in the electrical potential, okay, the difference in the electrical potential across the plasma membranes, the difference in the electrical potential across the cell membrane when compared to the outside, how much voltage difference is there inside the cell. This is called as, or this is the definition for the resting membrane potential. Again I am repeating, the definition is resting membrane potential is the difference in the electrical, potential or the difference in the voltage across the cell membrane in the resting state. We are always talking right now in this video, we will be only talking about the resting cells. We are not talking about the cells which are undergoing depolarization or repolarization. We are talking about the cells in their resting condition. Okay. Let me write the definition. Resting membrane potential is voltage difference between inside of the cell when compared to outside. Okay, now you will be still having a doubt, sir, I couldn't able to understand. Let me make it clear for you. Okay, so now imagine I am taking one cell. Okay, I am taking one cell. Here is a cell membrane. You can see there is inside the cell and outside the cell. Now what am I taking is a voltmeter. Okay, I am going to take a voltmeter. Now this voltmeter is going to show me the voltage. Now this voltmeter, it is connected with the electrode. So one electrode, the reference electrode, I am going to keep it outside. Okay, in comparison to the outside, how much voltage difference is there inside the cell? There is one more electrode which I am keeping here inside. There is one more electrode, let's say here. So how much difference is there? It's going to show some difference. So that difference in the voltage is called as resting membrane potential. And so what is the usual range of resting membrane potential? The range of resting membrane potential can be anywhere between minus 10 millivolts to minus 90 millivolts. So usually our human cells, they have a range of resting membrane potential. Different cells in our body have a different resting voltages. Okay, but one thing you have to observe here, our cells are having negative resting membrane potential. Our cells are having negativity. So when compared to outside, okay, when compared to outside, our cells are having this negative value. The voltage within our cells is negative. And why is that? Okay, we'll discuss. Now, here some important MCQs which I want you to know. See, first of all, our cells are very small. Okay, you can't see them. You can only see them under the microscope. So in order to pierce this cell, okay, you have to use such a micro electrode. Okay, you have to use an electrode. You have to keep this electrode into the cell so that the electrode should be very small. So it's a micro electrode. Okay. Now question is, this micro electrode, it is filled with which solution? See, this micro electrode, it is actually filled with a solution. Which solution is present? KCl, potassium chloride solution is present. Okay, this is a single liner question you should know. Okay, the electrode that is used to measure the voltage is the micro electrode, and the micro electrode is filled with a solution called as a potassium chloride solution. Okay, and see, because of the movement of ions, you know, our cells are having the leaky channels, voltage gated sodium channels, potassium channels, chloride channels, different channels are there. Because of the movement of the ions across the cell membrane, the resting membrane potential can change. The resting membrane potential, it can go to the threshold potential. From there, it can go to the depolarization, repolarization. The voltage can change. So, for the graphical representation, means you want to graphically record this voltage changes. Okay, then what type of electrode is used? Okay, see, there is something called as cathode ray oscilloscope. Okay, cathode ray oscilloscope is used for the graphical representation of the resting membrane potential. Okay, now you will be having a doubt, sir. First of all, what is the reason for the development of this resting membrane potential? Why our cells are having this negative resting membrane potential? We will discuss that now. Okay, so what creates, take the heading, what creates the resting membrane potential? Who creates this resting membrane potential? Okay, now the number one reason for the development of the resting membrane potential, the number one reason is concentration difference. Concentration difference, or you can say uneven distribution. Concentration wise there is a difference or uneven distribution of the ions when compared to the inside, when compared to the ICF. In ECF the ions are different. Okay, there is uneven distribution of the ions. Okay, so concentration difference are uneven. Uneven distribution of ions between ICF, that is intracellular fluid, and ECF, extracellular fluid. Now we will be having it out. So why this concentration difference is there? Okay, yeah, I am telling you the ions are having a different concentration. Okay, the outside the cell when compared to the outside the cell, inside the cell, like there is a concentration difference. Okay, now what is the reason for this uneven distribution of the ions? See, the two important reasons, that is due to something called as Donnan effect. Okay, actually the Donnan effect is the one which is going to maintain, to be very frank. Okay, so when the cells develop, okay, in the development stage itself there is uneven distribution of the ions, and this Donnan's effect is going to maintain that uneven distribution. Okay, it's going to make sure that these ions are unevenly distributed. That uneven distribution of the ions is due to or maintained by this Donnan's effect. Don't worry, I will explain you what exactly is Donnan's effect. Okay, and this is the reason number one. And one more reason for this uneven distribution of the ions is selective permeability. Okay, selective permeability of cell membrane. For ions. See, what does I mean by the word selective permeability? Means the cell membrane is designed in such a way it is only permeable to certain ions. Okay, even during resting stage the cell membrane is permeable to only certain type of ions. Certain type of ions are freely passing across the cell membrane and certain type of ions are not passing across the cell membrane. So because of this differential permeability or selective permeability, the ions are unequally distributed, okay, across the cell membrane. Okay, this is one of the reasons. Next I will explain you the few more reasons for the development of the resting membrane potential. One I have told you, it is because of the uneven distribution of the ions. Next one is potassium efflux via potassium leaky channel. So this is the most important reason, the potassium efflux via the potassium leaky channels. Okay, I will explain you this. And one more reason is sodium potassium ATPase. Okay, the sodium potassium pumps or sodium potassium ATPases, they are actually electrogenic pumps. Electrogenic pump. Now in the name itself it's there, electrogenic. What is the meaning of the word electrogenic? It is going to generate this electrical voltage. Okay, it's going to cause this uneven difference in the voltage. How? We'll discuss that. Okay, first let me start our topic with the Donnan's effect. So what exactly is this Donnan's effect, sir? Because this is very easy. Potassium efflux, potassium is always trying to go out of the cell. Okay, let me tell you. Okay, for easy understanding purpose, let me explain you about this potassium in a simple way. Later I will explain in detail. See, our cells are always okay, like permeable to potassium. Potassium, even during the resting state, potassium is always going outside the cell. If you see a cell here, these cells are having leaky channels. These leaky channels means they are working even during the resting state. So, potassium from high concentration is always going out, always potassium is going out, as the positive charges are going out of the cell. 24/7 this is happening, as the positive charges are going out of the cell. That is going to cause the negativity inside the cell. Okay, that is going to cause the negativity inside the cell. So, the potassium efflux is the major contributor, I should say, the major contributor for the development of the resting membrane potential. Okay. Next, what exactly is this sodium potassium ATPases are doing? Guys, look at here. Here is one cell, and imagine there is this sodium potassium pump over here. See, the sodium potassium ATPases are pumps. What they will do? They are going to throw 3 sodium ions out of the cell. 3 sodium is going to go out, and in exchange only 2 potassium is coming in. So, there is a net loss, right? Net loss. Okay, 3 positive charges are going out, but only 2 positive charges are coming in. So, there is a net loss of positivity. So, this is also going to contribute to the development of the voltage difference, because more positivity is going out and less positivity is retained in. So, that is also going to create this voltage difference across the cell membrane. But whatever the resting membrane potential that is developed due to the sodium potassium ATPases, its maximum, let's say, only 5 to 10%. Okay. But the main reason for the development of the resting membrane potential is due to the potassium efflux. Always potassium is going out, positive charges are going out, that is going to create the negativity inside the cell, because the cell is losing the positivity, positive charges are going out. Okay, we will discuss that in more detail, okay, later. But now the most important thing, okay, most of the students, they find it very hard to understand what is this Donan's effect or this equilibrium. Okay, let me explain you about the Donan's effect now. Okay, Donnan effect. So, what exactly is this Donnan's effect? Donnan's effect will tell you why there is this unequal distribution of the ions. Okay. First of all, you need to understand, see, imagine here there is a cell. Okay. Now, inside the cell, what do we have? ICF. Okay, ICF. And outside the cell, there is ECF, extracellular fluid. The cells are developed in such a way, in the beginning, the development of the cells itself, outside the cell, there is more sodium chloride present. Okay, sodium chloride is nothing but the salt water. So, we usually say something like this. The cells, see, when the cell is, see, first tell me, in the evolution wise, when the cells are developing, okay, the life originated in the sea water, right? Life originated in the sea. So, even now, the cells want to keep the same kind of environment around them, the same sea water environment. So, our extracellular fluids are more similar to the sea water. That is the reason why there is more sodium chloride outside the cell and less sodium chloride inside the cell. Okay. So, inside the cell we have more potassium. Inside the cell we have more proteins. Okay. But outside the cell we have more sodium chloride. So, always remember, life or cells. Okay. Cells are life originated in seawater. Okay. So, ECF, okay, have similar composition to seawater. Okay. So, that is rich in sodium chloride. Okay, the ECF is rich in sodium chloride. Now, so now you understand, in the beginning itself there is unequal distribution of the ions. Sodium is more outside the cell, chloride is more outside the cell, calcium is more outside the cell. There is unequal distribution of the ions. Now you might be thinking, sir, the ions are unequally distributed, no? But we know according to the law of equilibrium, they should be like, equilibrated. The sodium from outside should come in and there should be a balance, and potassium should go out and it should be equally distributed. Why this is not happening? Okay, so why the equilibrium is not happening? Okay, that will be explained by the Donnan's effect. Students, for this, let me take two compartments. Okay, here I am taking two compartments. Let's say compartment number A and compartment number B. Now I am going to keep sodium. Okay, I am keeping sodium here. How many molecules of sodium or how many ions of sodium? Let's say 9 sodium ions. Here also I am keeping 9 sodium ions. Okay, 9 sodium ions equally distributed. So tell me, will there be any further movement of the sodium from here to here or here to here? No, because they are equally distributed. There is not going to be net movement. Now I am going to keep chloride here. How many molecules of chloride? 9 molecules of chloride I am keeping here. Okay, only in compartment number B I am keeping the 9 molecules of chloride. So you tell me now what this chloride want to do. Look now. So let me duplicate this. Now chloride, okay, is going to diffuse and it's going to organize itself, okay, in an equilibrium, okay, into an equilibrium. So now here 4 chloride are going to be there, some chloride will come to this side, okay, here also 4 chloride are going to be there, and tell me 4 plus 4 how much? 4 plus 4, it is 8, but I kept 9 chloride, right? So 1 chloride ion is going to move in both the sides, like according to the concentration from this side to this side, and from sometime from this side to this side, it is kept on oscillating, it is kept on moving. Okay, so now we came to a equilibrium state. Now, so students will have a doubt, sir, yes, this is what is equilibrium, and we know what exactly is equilibrium. Means equal distribution of the ions. Why such equilibrium is not happening in our cells? You told us sodium is more outside the cell, potassium is more inside the cell, and why that equilibrium is not getting attained? Why they are not reorganizing themselves? Even though, okay, more sodium chloride is outside the cell, why it is not coming into the cell? And why the potassium is not completely going, and like why that equilibrium is not attaining? That is because of the Donnan's effect. Okay, now why? What is the Donnan's effect? Let me explain you. Okay, again let me take the same two compartments. Okay, A and B. Same, I am keeping 9 sodium ions and 9 chloride ions. Now when I keep 9 chloride ions, 4 chloride ions are coming here. 4 chloride ions are coming here, and 1 chloride ion is kept on oscillating here and there. Now, for the first time, I am introducing a large impermeable molecule. The word is important, large impermeable ion or impermeable molecule, which means this membrane, whatever is there, it's not permeable for this particular substance. What is the substance that I am taking here? Proteins. Okay, now I am taking proteins. Now these proteins are also negative charged. Now I am keeping 9, let's say minus 9. Okay, proteins are negative charged and I am taking 9 ions. Now tell me, do you think these proteins are permeable? No. So in the presence of this, listen carefully, in the presence of this large impermeable molecule, do you know what will happen? The arrangement of these permeable ions will change. Okay, the distribution of these permeable ions will be affected. How, sir? Let me tell you. Okay, so how equilibrium? Definitely at the end of the day there should be an equilibrium. So how the permeability of the ions will be affected? Now look carefully how the equilibrium is going to attain. Let me duplicate this. Now look carefully. Sir, what exactly is going to happen? Let me first erase these ions now. Okay, now tell me how many proteins I kept here. Let's say 9 molecules, right? 9 molecules. See, these are negative charges. These proteins are negative charges. So these negative charges, okay, are going to attract more positive charges towards them, and the negative charges are going to repel the negative charges. Okay, these negative charges are going to affect the permeability of the sodium ions, are going to affect the distribution of the chloride ions. They are going to affect the distribution of the sodium and chloride ions. How, sir? These negative charges, these proteins, will attract more sodium ions because sodium charges are positive. They are going to attract more sodium, and they are going to repel more chloride because chloride is a negative charge. So in the presence of these proteins, Look, how many sodium is going to be there here? 12. And how many sodium here? 6. How many chloride here? Chloride is decreasing, see, 3. How many chloride here? 6. Now, previously look, this is equilibrium condition, this is equilibrium. Okay, see before in the starting, okay, this is how the equilibrium is. In the beginning, this is how the equilibrium is. Equal distribution, sodium equally distributed, chloride equally distributed. Okay, but look, when you introduce these proteins, when you have introduced these proteins, the distribution of this permeable ions is altered. So now here 12 came, 12 sodium is there. Now why is more sodium, more positive charges are there? Because more positive charges, because these negative charges are absorbing more positive charges, attracting more positive charges. Okay, so now look carefully. Okay, now based on this, we are going to give an equation. Okay, that is called as Gibbs. Okay, now here you will be getting more clarity. Okay, why I am calling it as an equilibrium. Okay, how can this be an equilibrium state? That can be explained with Gibbs Donnan's equation. Okay, so what exactly is this Gibbs Donnan equation is telling us? Okay, that is the total positive charge in the compartment number A. Okay, the total number of positive charges, look, how much total positive charges are there in the compartment number A? 12 is exactly equal to the negative charges in the compartment number A. That is 9 plus 3, how much? 9 and 3, this 9 plus 3, these are the negative charges. Chloride is a negative charge, protein is a negative charge. So 9 plus 3 is how much? 12. Okay, the amount of positivity, the number of positive charges is equal to the number of negative charges, right? The total positive charge in compartment number A is exactly equal to total negative charge in compartment number A only. Okay, now exactly same is true with the compartment number B also. How much positive charge is there? Positive charge is plus 6. And how much negative charge is there? Minus 6. So positive charges and negative charges are equal in number. So right, total positive charge in compartment number B is equal to total negative charge in compartment number B. Exactly, positive charges, negative charges are equal. So can I say this compartment number A is electron neutral because the charge wise they are equal, positivity and negativity is equal. It's an electron neutral compartment, and compartment number B is also electron neutral. Okay, because the number of positive charges and the number of negative charges is equal. So there is electron neutrality. Okay, next, the product of, now I am going to multiply, this is the first one. Okay, in Gibbs Donnan equation, this is the first point. The second one is the product of permeable ions in compartment number A. Okay, so the product means multiplication. The product of permeable ions in compartment number A is equal to same product of permeable ions in compartment number B. Let me prove this for you. Tell me, in compartment number A, which permeable ions are there? Sodium chloride ions are there. Sodium chloride. Okay, so sodium into chloride. How many sodium ions are there? I have told you 12 sodium ions are there. And how many chloride ions are there? 3. So 12 into 3, how much? 12 3 is a 36. So this is the product. 12 3 is a 36. In the same way, here in compartment number B, what is the product? Same sodium chloride ions are there. How many sodium chloride? 6 and 6. I have shown you. So 6 into 6, how much? That's also 36. So the product of the permeable ions, I am not talking about the impermeable ions, the product of the permeable ions in the compartment number A is exactly equal to the product of permeable ions in the compartment number B. Okay, same number of ions are there. Okay, that is, which means the equilibrium state, they are equally distributed, the ions are equally distributed, the ions are equally distributed. Okay, next one more important thing. Okay, here difference is there. What is that? Osmolarity. You look at the number of ions. See, in compartment number A, more number of ions are there. In compartment number A, more number of ions are there. But in compartment number B, less number of ions are there. 6 plus 6, only 12 ions. But here see, more number of ions are there. So, the more the ions, the more the number of ions, the more the osmolarity. So, definitely compartment number A is having more the number of ions and more the osmolarity. Okay. So, right. Osmolarity in compartment A is greater than B because A is having more ions and B is having less number of ions. So, at the end of the day, what I am trying to explain you is why there is unequal distribution of ions. That is because of the Donnan's effect. And again I am telling you what exactly is the Donnan's effect. In the presence of impermeable molecules like proteins, in the presence of impermeable molecules like proteins, the moment you add these proteins, the distribution of the permeable ions will be affected. Okay, will become uneven. The moment you add, say, the moment you add these proteins, in our cells proteins are there or not? Yes, in our cells proteins are there. The moment you keep the proteins, the distribution of these ions is affected. The sodium which was supposed to be 9, it became 12. Okay, see, previously 9 and 9 equally distributed, but now here 12 sodium is there, here outside only some in the compartment number B only 6 sodium is there. Okay, so in the presence of these proteins or any large molecules, any large impermeable molecule, the distribution of the ions will be affected. Okay, so that is what is the Donnan's effect, and Donnan's effect is telling us why the ions are unequally distributed. Okay, in our cell. Next step. Having said that, now let me explain you. You already know this, but let me explain you. See, here I am showing you a cell. Let's say this is a cell, which means here I am talking about the ICF, intracellular fluid, and outside ECF, extracellular fluid, intracellular fluid, extracellular fluid. Now, here if I take this as compartment, one of the compartment, and here it's the outside is a different compartment, 2 compartments. Now, I have told you in one compartment we can have more number of ions, more number of positive charges, but the number of positive charges is exactly equal to the number of negative charges. So, this compartment is electro neutral. Okay, this is electro neutral. Now, outside say less number of ions are there. Okay, let's say less number of ions are there, but the number of positive charges is exactly equal to the number of negative charges outside also. Okay, in the other compartment also maybe less number of ions are there. So, outside compartment is also electro neutral. Okay, so outside is electro neutral, inside is also electro neutral. There is no any difference in the distribution of the charges. The number of positive charges is equal to the number of negative charges inside as well as the outside. Now, you will be having it out, sir, outside electro neutral, inside electro neutral, no. Then why there is a difference? Now, can you see why there is a difference in the voltage when compared to the outside? See, outside you say the number of positive charges and number of negative charges equal. The number of positive charges and number of negative charges equal. Then why there is this resting membrane potential? Why there is a voltage difference? Okay, inside the cell when compared to the outside? That is because of the concentration gradient. Here, more number of ions are there. Here, the less number of ions are there. Okay, more number of ions are there here. Here, less number of ions are there. Let me take you examples. Okay, now let's take an example of a human cell. Okay, now here I am showing you one human cell. Okay. See, in human cells, there are different types of ions. Okay. But what's the major ion inside the cell? The major ion inside the cell is potassium. Okay. So here I am taking lot of potassium inside the cell. Lots and lots of potassium ions are there. Along with these potassium ions, their negative ions also will be there, because I have told you every compartment is a electroneutral compartment. Okay, the number of positive charges should be exactly equal to the number of negative charges. Now, I am going to take here potassium leaky channels. See, human cells, they have different types of leaky channels, but the most important leaky channel that we have is the potassium leaky channel. Potassium leaky channels are more in number in human cells. Okay, sodium leaky channels, calcium leaky channels, chloride leaky channels, they are also there, but mainly potassium leaky channel I am taking. Okay, now potassium is also there outside the cell. So here is also potassium and their respective negative charges are also there. You tell me, outside is an electroneutral compartment, inside is also electroneutral compartment, but what about the concentration gradient? Okay, see, voltage wise, let's say, okay, now at this state, voltage wise 0, 0, electroneutral compartment, but there is uneven distribution of the ions. More number of potassium, less number of potassium, more ions, less ions. So because of the concentration gradient, the potassium will start to go out. So these potassium leaky channels are allowing the potassium to go out. Okay, but these are leaky channels, they are selectively permeable. Okay, our cell membrane is selectively permeable, which means it is allowing only the potassium to go out. These leaky channels are allowing the potassium to go out, but not these negative charges. So now this potassium is going out, but do you think it's a negative charge? Is it going to go out? No, definitely not. So the potassium ions, because of the concentration gradient, potassium ions are going out, but the negative charges are not going out. So that is going to lead to the negative resting membrane potential. Okay. So now you understand why there is a negative resting membrane potential, why the potassium is going out. Potassium is going out because of the concentration gradient. There is more potassium inside the cell, there is less potassium inside the cell. Okay, there is the potassium ions are unevenly distributed, and why there is uneven distribution? That is because of the Donnan's effect. I have told you. Okay, that Donnan's effect is going to cause the uneven distribution of the ions. Okay, because of the uneven distribution of the ions, potassium is going to go from the high concentration to low concentration. But only potassium can go because the cell membrane is selectively permeable. They are leaky potassium channels. They are not letting the other negative charges to go out. So as it is selectively permeable, potassium is going out, doesn't allowing this negative charges to go out. So cell is becoming rich in negative charges. So the cell is going to become more negative. Okay. So let me write two statements here which are very, very important. So concentration gradient allows movement of potassium out of the cell. Okay. So because of the concentration gradient, potassium is going to go out. But till how much time? Do you think all this potassium can go out? No. Till how much time? See, as this potassium is going out, you tell me after some time what will happen? There is going to be development of more negative charge. Now this negative charge is going to be so much. After some time, the negative charge will become so much, it doesn't allow the potassium to go out. Okay, because this negative charge is going to attract the positive charge, and this doesn't allow the potassium to go out. Okay, and whatever the positive charge that is developing over here, because of the potassium efflux, whatever the positive charge that is developing over here, this positive charge doesn't allow the positive charges to come out, because positive charges will repel the positive charges. So after some time, what will happen? There is going to be an equilibrium state. The potassium, the net movement of the potassium will stop. Okay, because of this electrical gradient. So write electrical gradient after some time, electrical gradient oppose movement of potassium out of the cell. Okay, so now tell me what happened finally. Okay, so now these negative charges are not allowing the potassium to go out. So now my question to you, because of the movement of this potassium, okay, because of the movement of this potassium, what we have developed? some voltage difference has developed. Inside the cell, negativity is there. This is called as equilibrium potential of the potassium ion. Okay. Now, first let me write what exactly is the equilibrium potential or equilibrium. Okay, what exactly is this equilibrium potential or equilibrium? Equilibrium potential means the net moment of the ions, net moment of potassium through leaky channels is going to be 0. So, the moment potassium leakage, the moment the potassium efflux stops, then we are going to call it as a equilibrium attained. The net moment of the ions is going to be 0. And why that is happening, I have told you. Okay. Now, look guys, look at here, look at this cell. Now you tell me, let us say potassium I am keeping here, some amount of potassium. Okay, anyway potassium is more inside the cell along with its respective negative charges through the leaky potassium channels. Potassium will start to go out. Okay, potassium will start to go out. After some time, the potassium efflux will stop. Okay, potassium efflux will stop and cell is going to have this negativity. Okay, as some potassium charges has gone out, cell will become more negative. Now at this condition, now you are going to measure the voltage across the cell membrane. Now you are going to measure the voltage across the cell membrane by keeping a reference electrode outside and by keeping one more electrode inside. Now you are measuring the voltage difference. This voltage difference is called as the equilibrium potential. Means the voltage in this cell now at a equilibrium state. So write voltage difference, okay, which present during equilibrium condition of cell. Okay, the voltage difference which present during the equilibrium condition of a cell is called as equilibrium potential. Also called as isoelectric potential. Okay, guys, don't confuse this with the resting membrane potential, because resting membrane potential is different and equilibrium potentials are different. Why? Because right now I am only talking about the one ion, potassium. Okay, so resting membrane potential is due to different leaky channels and different ion, like leakage. Right now I am only talking about the equilibrium potential of this potassium. Okay, because of the potassium efflux. Because of the potassium efflux, yes, cell is getting negativity. But do you think only potassium can go out? No, some ions are also coming into the cell. So that is resting membrane potential. Right now I am talking about the equilibrium potential. Okay. Now, what is the formula to calculate the equilibrium potential, sir? Okay, first of all, we will discuss about the resting membrane potential later. Right now what we have discussed about the equilibrium potential. Okay, and the ion that we have taken as an example is the potassium ion. So now, formula to calculate equilibrium potential. Okay, the formula is called as Nernst equation. Nernst, or some will call it as a Nernst equation. So what exactly is this Nernst equation telling you? Nernst equation is used to calculate the equilibrium potential. Okay, EQ stands for equilibrium potential. The formula is RT ZF log, natural logarithm, log the concentration of ions outside the cell divided by the concentration of same ion inside the cell. Okay, the concentration here, X stands for the concentration of the ion outside the cell and the concentration of ion inside the cell. So this particular ion is creating how much equilibrium potential? Because of this particular ion, how much equilibrium potential is getting generated? Okay, is it going to create minus 60, minus 70, minus 80, minus 100, minus 5, minus 10, minus 20 inside the cell? How much is it creating? Because of this ion, how much voltage is getting generated inside the cell? Okay, that is called as the equilibrium potential of this particular ion. Now, see, this is the natural logarithm. Now, let's convert into log base 10. So, for that, I am going to change the equation to EQ, equilibrium potential is equal to same. Equilibrium potential is equal to 2.3. Now, I have to multiply it with 2.3 into RT/ZF log base 10, same concentration of ions outside the cell divided by concentration of the same ion inside the cell. Now, this RT by F, okay, it's having a value. Okay, this RT by F, the value of RT by F, okay, is going to be constant value. It changes according to the room temperature. The RT by F value, okay, let me write it here. RT by over F value at room temperature 26.7 millivolts. So, you can take it as a constant, okay, this value. So, I am going to replace RT by F with 26.7 millivolts. So, now rearrange equilibrium potential is equal to 2.3 into 26.7. Now, I am going to take it as 61 millivolts by Z. Okay, I am not changing anything. The Z is Z. Z is the valency of the ion. Okay, valency of the ion. Z log base 10 concentration of ion outside the cell divided by the concentration of ion inside the cell. Okay. Now, what exactly is this Z, sir? Z is the valency of the ion. Valency of that particular ion. Is it if it is a sodium plus 1, if it is a chloride minus 1, something like that. The valency, calcium plus 2. Okay, the valency, whether it's a positive charge or negative charge. Okay. Next step. Now, let me give you an example. Okay, let me give this is the final equation. Okay, this is the final equation. So, if with example, you will understand it better. How to calculate the equilibrium potential of this one particular ion. This one particular ion is creating how much voltage. Okay. Now, the example, let's write here. I am taking a cell. Potassium. Okay, I am talking about the potassium. Now, we are going to calculate the equilibrium potential value of this potassium in this particular example. Okay. Potassium, let's say 140. Okay, 140 potassium inside the cell. 140 millivolts. Okay, 140 millivolts. Outside the cell, the concentration is 14. Okay, millimoles per liter. Okay. Now, according to our formula, that is Nernst equation, 61, okay, millivolts divided by Z. What is the valency of potassium? Potassium is a positive charge, so plus 1 divided by 1 into log base 10 concentration of ion outside the cell divided by the concentration of ion inside the cell, that is 140. How much it will become? So, 61 over 1, the value will be 61 only. 61 log base 10 1 by 10. Okay, 1 by 10. Now, you tell me 1 by 10 means how much? It's a 0.1. 61 log base 10.1. What is the log value? Log base 10 0.1 value is going to be minus 1. Okay, the value is minus 1. 61 into minus 1. So, 61 into minus 1 is going to be minus 61 millivolts. So, this is how to calculate the equilibrium potential of an ion. So, in this particular example, we have calculated the equilibrium potential of the potassium. Okay. So, potassium, it is going out because of the concentration gradient. See, it will definitely go out and it will create a voltage of how much? Minus 61 inside the cell. This is just an example. Okay. Let me give you one more example so that you will understand better. Now, here, let me take chloride ion. Okay. So, we know chloride inside the cell is definitely going to be less. Let us say 11. Outside the cell, there is more chloride, 110. Okay. These are just reference values. Now, I am asking you to calculate what is the equilibrium potential of this chloride. This chloride is going to generate how much negativity inside the cell, how much voltage difference in this cell membrane, okay, when compared to outside. So, equilibrium potential of this chloride ion is equal to 61 divided by Z log base 10 into concentration of ion outside the cell, that is 110 divided by inside the cell. So it will become 61 by minus 1, definitely the valence is minus 1, chloride is a negative charge, so minus 1 into log base 10 going to be 10, right? So 11 tens are 110, so 10. Log base 10 into 10, what is the value? That is minus 61 into 1, okay, minus 61 into 1, because log base 10 over 10, okay, log base 10 value is going to be 1, so again minus 61 millivolts. So even this chloride, okay, in this particular example, this chloride is also going to generate a value of minus 61 millivolt. Okay, the equilibrium potential of the chloride in this particular example is minus 61 millivolts. So finally, I am going to give you the proper equilibrium potential. These are just examples. Okay, the equilibrium potential of the chloride is not going to be 61. In this particular example, it is 61. So now I am going to give you a list of ions with their proper equilibrium potentials. Okay, equilibrium potential of different ions. Equilibrium potential of different ions. Let's say sodium, chloride, potassium. Equilibrium potential of calcium. So what is the equilibrium potential of the sodium? The equilibrium potential of the sodium is plus 63 millivolts. So sodium is always trying to create this much voltage inside the cell, okay, plus 63 millivolts. Okay, inside the cell always, because of the movement of the sodium wants to create a voltage of how much? Plus 63 millivolts, because sodium is a positive charge. Chloride wants to create minus 70 millivolts. Potassium wants to create minus 90 millivolts. This is very important MCQ. And calcium wants to create a voltage of plus 132 millivolts individually. Okay, but let me ask you, do our cells have only sodium? If only sodium is there, sodium is trying to create a voltage plus 63. If only potassium is there inside the cell, the potassium will try to create a voltage of minus 90 millivolts. But no, our cells are having all these ions. So all these ions, okay, they want to create their own equilibrium potential. So finally together, when they come up, they will come up with a value of resting membrane potential. Okay, equilibrium potential is calculated by an equation called as the Nernst equation, and equilibrium potential is for the one particular ion. Okay, let me give you an example. Say if a membrane is permeable to only one particular type of ion, let's say this is this one cell membrane. Okay, there is this one cell membrane, and in this cell only, let's say potassium is there, hypothetically only potassium is there, and it is having this potassium leaky channel. Inside the cell there is more potassium. We know potassium is more inside the cell, and outside the cell there is less potassium. In this hypothetical situation, only potassium is there, so potassium wants to go out, and potassium is creating its own equilibrium potential. Okay, how much it wants to create? Minus 90 millivolts. Okay, potassium wants to create a value of minus 90 millivolts. Now in this particular condition, the equilibrium potential of the cell is exactly equal to the resting membrane potential, because no other leaky channels are there, no other ions are there. So in such a hypothetical condition, the equilibrium potential of the cell is exactly equal to the resting membrane potential. Okay, so let me write, if membrane is permeable to only one type of ion, then resting membrane potential of that cell is equal to equilibrium potential. Okay, equilibrium potential of that particular ion. Okay, now my question is, then how to calculate the resting membrane potential of a human cell? Okay, resting membrane potential of a particular cell. See, resting membrane potential, it is not only dependent on the potassium, but it is also dependent on sodium, chloride, magnesium, calcium and other ions. Okay, so how to calculate the resting membrane potential? Calculation of resting membrane potential. There is a different formula for this. Okay, to calculate the equilibrium potential, we have used the Nernst equation. But for the calculation of the resting membrane potential, the formula that I am going to use is called as Goldman, Hodgkin's, Katz equation. Okay, so Goldman, Hodgkin, Katz equation is used to calculate the resting membrane potential. And what is this equation, sir? See, the voltage across the membrane. The voltage across the membrane is equal to RT by F log. Okay. See, pK stands for the permeability coefficient. Okay, permeability coefficient of potassium ion outside the cell plus permeability coefficient of sodium outside the cell plus permeability of chloride inside the cell divided by permeability of potassium inside the cell, permeability of the sodium inside the cell plus the permeability of chloride outside the cell. So, this is the formula. It is a very simple formula. What we are taking is the permeability of the potassium, okay, permeability as well as the concentration. Okay, so this P stands for the permeability and here the K stands for the concentration. The concentration of potassium outside the cell and the concentration of potassium inside the cell. Means we are taking consideration of the different ions, because right now we are talking about the resting membrane potential. So, resting membrane potential is dependent on different ions. So, we are not only considering the potassium, we are also considering the sodium chloride, okay, outside the cell in comparison to the inside the cell. Okay. So, here we are also taking one more thing, constant, that is called as the permeability. What is the permeability? The permeability of these ions. Okay. So, finally what I am trying to say for your exams, just remember Goldman-Hodgkin's Katz equation is used to calculate the resting membrane potential or the voltage difference across the cell membrane. Nernst equation is used to calculate the equilibrium potential of an individual ion. Nernst is for individual ion. Goldman-Hodgkin's Katz is for the resting membrane potential. Okay, the resting membrane potential is dependent on all the ions together. Okay. Now, let me give you a summary of resting membrane potential of different cells in our body. Resting membrane potential of different cells. See, different cells have different number of the leaky channels. Some cells may have more potassium leaky channels, some cells may have more chloride leaky channels, some cells may have more sodium leaky channels. Depend on the number of these leaky channels, okay, specific leaky channels, the resting membrane potential can change. So, what is the resting membrane potential of a neuron? The resting membrane potential of the neuron is minus 70 millivolts. If they ask you about the skeletal muscles, the skeletal muscles is going to be minus 95 millivolts. Smooth muscle is going to be minus 60 millivolts. See, these are the values that you need to just by heart. Neuron resting membrane potential minus 70 millivolts, skeletal muscle minus 95, smooth muscle minus 60 millivolts. Okay, cardiac muscle or cardiac myocytes is going to be minus 90 millivolts. The hair cells in cochlea is going to be in a range of minus 15 to minus 40 millivolts. RBCs minus 8 to minus 12 millivolt, and photoreceptors okay. So, during light stage and dark stage, let me first talk about the dark conditions. The voltage is going to be minus 40 millivolts, and during light, okay, whenever they are in light, that is during morning, okay, the voltage is going to be minus 70 millivolts. Okay. So these are the resting membrane potentials of different cells in our body. So finally, let's look at the recap from the beginning. What and all we have discussed. What is the resting membrane potential? The resting membrane potential is the voltage difference across the cell membrane when compared to the outside. Okay, how much is the voltage inside the cell? Most of the time it is going to be negative, and it's in the range of minus 10 to minus 90 millivolts. And okay, to measure this voltage difference, you should use a microelectrode, and the microelectrode is filled with which solution? Potassium chloride. For the graphical representation of this resting membrane potential, you can use the cathode ray oscilloscope. And what is the reason for this resting membrane potential? The reason for the resting membrane potential is due to the uneven distribution of the ions, and that uneven distribution of the ions is maintained by the Donan's effect. And what is the Donan's effect? I have told you the Donan's effect is in the presence of a large impermeable molecule, the distribution of the permeable ions will become uneven. Okay, so that is what is the Donan's effect. And according to this Donan's effect, I have told you, finally we have derived the Gibbs Donnan equilibrium. So what is the Gibbs Donnan equilibrium? The Gibbs Donnan equilibrium is telling you that the number of positive charges is exactly equal to the number of negative charges in the compartment number A as well as the compartment number B. Both the compartments will become the electron neutral compartments in the beginning. Okay. Next, the product of the permeable ions in the compartment number A is exactly equal to the product of the permeable ions in the compartment number B. Okay. Next, because of this Donan's effect, one of the compartment is going to have the more number of ions and the other compartment is going to have the less number of ions. That is going to create the osmolarity difference. One compartment is going to have the more osmolarity because the more number of ions. Okay. Next, see, now I am going to explain you about the equilibrium potential. What is the equilibrium potential? Equilibrium potential is the voltage created by the one particular ion. Because of the diffusion of this one particular ion, how much voltage is created? Every ion will have its own equilibrium potential. Okay, I have given you potassium will have its own equilibrium potential minus 90 value, sodium will have its own value, chloride will have its own value, okay, calcium will have its own value. That is the equilibrium potential. Equilibrium potential is calculated by the Nernst equation, but the resting membrane potential is calculated by the Goldman-Hodgkin-Katz equation. Okay, that yes, the topic is a little tricky topic, but very important for the exams. So with this, we have completed the topic of the resting membrane potential. Hope the video is helpful. Thank you.